Hello, I've decided to do a video response to your question because it required quite an intricate diagram. And so I started by writing out exactly what the integral was, 0 to 1, x squared to 2 minus x, x, y, dA. And I've drawn it out here. And so we have, starting from the outside um, part, we have 0 to 1 from dx, and these go from the bounds of the graph of y equals x squared, as shown here, and 2 minus x, and they intersect at the point 1, 1, which is quite convenient. And so we see that this shaded area right here is our area of integration. And so when we're changing the order of integration, we always keep the area of integration constant. When we change it to dx dy, as we'll see later, we still want to maintain the same area. And so when we're changing our order of integration, we go from a dy dx to a dx dy. And so that means that we begin our differentials starting with dy, going along the y-axis. But we have a problem when we're trying to find the limits of integration for this region, and it is that along the x-axis, the distance we have to go from the y-axis to the x-axis, or these vertical lines that I'm drawing here, are not constant. As we see on this linear part, it's linear, and on this part, it's quadratic, or as we'll actually see, it's just square root. And so when we have our new limits of integration, we can start from 0 to 1 on the y-axis, and going from 0 to the square root of y, and it gives us this first term. And for our second term, we have 1 to 2 going from 0 to 1 minus y, our vertical regions, and giving us this second integrand. And so I'd say this problem is kind of tricky because we have multiple limits of integration, but I hope this helps.